The world of functions is very vast. Even if we only consider functions from the real numbers to themselves, giving a thorough explanations of all the types of functions would take a very long time. That being said, a few functions come up much more often than others in domains such as physics, biology, or even mathematics themselves. In this three-part video, I will describe the use and properties of the most commonly used functions and how to assemble them within the elementary functions. If we think of the most basic function, it would probably be a function that never changes, a constant function. Constant functions, described by f of x equal to some number a, don't change value regardless of which x we pick. Visually, they are straight horizontal lines when plotted, located at a y value of a. What if we then go ahead and tilt that straight line? We get a function of the form f of x is equal to ax plus b, called a linear function. But why? Let's start when x is equal to 0. The value of f of 0 is a times 0 plus b, or just b. If we increase x by 1, the value of the function changes, say by a number a. If we increase x to 2, the function increases by a again, and so on, making the overall quote-unquote height of the function equal to a times x plus b. If the function starts at 0, that is if f of x is equal to ax, then y is said to be proportional to x. Such a type of function comes into play in the grocery store. If you buy 1 apple, then it costs 50 cents. But if you buy 10 apples, it costs $5. The cost of your apples is proportional to the amount you buy. So far, we only have straight lines, but lots of real-world phenomena don't vary linearly. Take a bowling ball dropped from a high place. It will start falling ever and ever faster as you approach the ground. It's not going to fall always at the same pace. In this case, the function we're looking for is a quadratic function. Quadratics describe a shape called a parabola, which you may know from parabolic antennae, and it can either be pointed upwards or downwards. Equation-wise, we can form a quadratic function by adding a term in x squared in front of the equation of a line, leading us to f of x is equal to ax squared plus bx plus c, where a, b, and c are any real numbers. Those first functions form a bit of a pattern. We have some number times x to an integer power, plus some number times x to some other integer power, and so on. In general, functions following this pattern are called polynomials. Poly stands for many, and nomial stands for name, which makes no sense, but that's just how they're called. Back on topic. Why do we care about polynomials? Polynomials are easy to calculate compared to some other functions, especially for computers. They are also defined everywhere, since we can take any x to an integer power, and then multiply by some other number, and then do so again and add and multiply like that, for any x value whatsoever. Polynomials are also neat because they are continuous on the whole real number line. You have no cuts, you have no gaps, everything is smooth. In practice, all those properties put them in the nice guys category, which makes them useful for all kinds of approximations. Given a set of points, we can find a polynomial through them, then calculate values in between, called interpolation, or values outside the set of points, called extrapolation. We can also calculate weirder functions approximately using Taylor sums. All of these make it so that calculators and computers basically speak in polynomials. The smooth and neat nature of polynomials doesn't exist throughout all functions though. In the upcoming videos, we'll explore some other useful functions from other powers of x to ways we can invert some of the functions we've seen here to exponential and sine functions that are very used in physics. In the meantime, make sure to play with the functions on Desmos. I've included a link to each one of the functions seen here in the description. Cheers!